So, welcome back to LAFI', everyone. We now have a keynote session given by Dario Stein, who was until recently at Nijmegen. And so over many years, Dario's made, I think, some very important contributions to probabilistic programming, in particular theoretical and foundational questions. And so recently, he's been working on causal probabilistic programming, and so I'm very excited to hear what he has to say. Please go ahead, Dario.
Thanks, Hugo. So let's think back some hours to the beginning of LAFI'. So when I looked at the program, before I looked at the program, I thought this would be titled an invitation or an introduction to causal probabilistic programming, because this is something new and exciting that I want to get you guys invested in. But then I saw that we already have like lots of talks and things on it. So I changed the title and now say, it's already here, right? Causal probabilistic programming exists, and I will give you a welcome. I will show you what it is about and what are interesting questions and interesting challenges. And because this is very new, there will be lots of questions and challenges, and there's more things that I don't know than things I know. So I'll show you some things that I know, I'll show you some things that I care about, and then hopefully we can kind of go forward together and explore this paradigm. This contains some joint work that I've been doing with these people. This is the same collaboration that already Theo's talk was about with Cairo people. Cairo is a causal probabilistic programming language built on top of Pyro. And I'll talk a tiny bit about this, but this is more kind of the broad context of what we want to achieve. What do we want to achieve? So causality, is the field that asks about cause and effect relationships. And I've been trying to come up with examples, but that's kind of understating it. Any finite list of examples would understate it, because this is the essence of science, right? This is in any empirical question, this is in the end what we want to know, right? What can we change? Does this cause that? And then a lot of kind of everyday statistics that we do is on an observational level. We talk about correlations and not causes, and we've been kind of taught to correlation doesn't imply causation, right? But then what is causation and what does imply it? That's the whole purview of this field. So there's some classical questions, right? Like does this drug work? If it works, why does it work? Is it a direct cause, or is there some weird side effect which is instead why it works? Does smoking cause cancer? Or like very relevantly something like how much of the snow chaos can be attributed to climate change? Or according to Theo, I have a car, right? But I've actually taken the train, which could have gone very badly. So if I had taken a plane, would I have arrived at Rennes? Those are causal questions, and we want to answer them. Now, interestingly, very recently, also machine learning has been getting interested in this causal paradigm. So there's some screenshot of a framework, PyY, that has different frameworks and languages and libraries to kind of explore causality. Now stuff starts to pop up with large language models, for example, where we ask about counterfactual tokens. So LLMs themselves are bad with causal reasoning, but of course internally it's a causal process. So we can ask, hey, we saw this token here, what would have happened if, I don't know, the story you're writing, the person has a different name, would have that, what would that have affected? So there's interested also in this in kind of machine learning. And now, so to give you the broad overview, the study of causality goes back to Julia Pearl and his famous 2002 book, Causality. And what he does is, first of all, give a mathematical theory of what these things mean, because before that causality was a bit shunned, right? It's like, it's philosophy, it's not really statistics, it's not something you can calculate. But he can calculate, and for this he kind of classifies causal queries into what he calls a ladder, and it has 3 different rungs. And the most basic rung here is rung 1, that is traditional statistics. So those are all the questions that deal with just observing a situation as it unfolds. And if we observe, we can look at, I don't know, distributions, we can look at correlations, all this kind of thing where we leave a system unperturbed. That's the seeing level, the observational one. So an observational question would be, is smoking associated with cancer? Okay, we just collect data and then we compute a coefficient and fine. There we have it. But that's not a causal question. The causal question we want to ask is, does smoking cause cancer? And we cannot answer this just with associational data, because there's many different causal structures that are imaginable, which are consistent with those observations here, but they tell very different stories once we intervene. Intervening means I force a person to smoke, and like, how does that affect their life? Again, very unethical, but this is the type of question that we're actually interested in. Or I give a patient a drug, or I don't know, make a person drink alcohol. What does that affect? That's very different from just seeing that people who happen to drink alcohol also have other outcomes. So this interventional rung 2 here is really where talking about causes starts. Okay, why do I have an arrow here? Because the higher rungs project onto the lower ones, right? So from any causal situation, I can also get observational predictions, but I usually cannot go up. So I have lots of situations here that are consistent with something higher up, but I don't necessarily know how to infer stuff here unless I make assumptions, and then I sometimes can infer, and this kind of lifting problem is exactly what causal inference is about. And then there's a third rung, which is counterfactual reasoning. So this is not just changing something, but this is having observed something and then kind of imagining what could have happened if things were different. And this is very human, this is very interesting, because there we start imagining kind of different courses of history. And again, this is a mathematically separate rung, because again, there's many situations here, even if we know how they react to interventions, there may be different mechanisms at play that affect how they would behave under counterfactual questions. To really have these three kind of layers. So a typical counterfactual question, right? Like, I don't know, whoop. So I have never smoked, but I wonder if I had, what would have happened, or so on. So keep this picture in mind. There's 3 tiers, and I kind of want to take this and move it into programming, because probabilistic programming, as we have done it so far, is firmly on rung 1, right? It's a very nice, it's a very expressive framework. We love it. That's why we're here. But it conditions, and conditioning is not intervening. It's really here. So the question is, how can we lift? What even should go here or here? What's the kind of probabilistic programming that is enriched to talk about interventions or counterfactuals? And that's that's by definition what causal probabilistic programming is, but I want to show you how we can start doing it. So what I will do is first give you an outline about kind of Pearl's theory of causality. So this is the maths, this is how to do it by hand. And then I want to get into how to lift this into fully fledged languages. And because this is not solved, this is very open, right? I will talk about what are the goals, but also what are the difficulties, what kind of trade-offs are in there. Some mathematical facts. If you're a theoretician like me, I have lots of stuff, and I have these 2 symbols, right? So we have some insights that are already there, and they are cool, and then we have way more questions. So pay attention to these symbols and talk to me about them, because all of them can spawn off into research. So this is the recap. This is the kind of classic maths part of the story. If you open Pearl's book, and you would say, what do you need to answer these 3 rungs of the ladder is this. If you want to answer observational questions, you just need a Bayesian network. You need random variables, and they have a joint distribution, and you measure, and then you can answer all the statistical questions. If you want to answer rung 2 interventional questions, you need something called a causal Bayesian network. I will explain what that is. And but this is pretty intuitive. And if you want to ask counterfactual questions, then you need something that he calls a structural causal model. That's more specific. I will also explain what this is, but there I'm actually not sure if the we need this is actually correct, if this is the right formalism. It is a formalism that works, but yeah. But again, this is how Pearl would explain the story. Okay, so rung 1 is easy to explain. We just need a joint distribution, and then from the joint distribution we compute. And this is what probabilistic languages do very nicely. We sample, and then we condition or do any kind of inference. And in a Bayesian network, we have a bunch of these variables, and then we draw like a DAG structure on them. We draw arrows between them. But the arrows mean something very specific. So arrows, or absence of arrows, means that there are certain conditional independences that we assume, or that are valid in between this set of variables. So for example, if we draw a diagram like this, right, x to y, but there's a z in the middle, and I don't draw an arrow here, that means that x and y are conditionally independent given z. So if I condition here, then x and y become independent, so whatever influence there is kind of mediated by z. Except, as a Bayesian network, this diagram here is actually equivalent to this diagram, where I flip everything around, because that's the same conditional independence relations, right? It still says x and y are separated once I can condition on z. So this is important to keep in mind. On rung 1, these DAGs just talk about conditional independences. They don't talk about a causal flow of information, because we're on rung 1. It's not causal. If we want to read this causally, we need to go to rung 2, and then it means what you actually think it means, right? So in a causal Bayesian network, it looks the same way. We draw it the same way, but now the interpretation is very different. The interpretation says, here, if I draw a link between variables, there is at least a possible direct causal influence. And then there's kind of these transitive influences, so x can influence y, but only mediated via z. And under this interpretation, this structure here is different from this structure, because here, well, y listens to x, and here x listens to y, and not the other way. So this is very important. But if we just observe distributions that are induced by this, we can't tell the difference. We cannot tell causal structures usually by just projecting out and looking at correlations. But we can distinguish these two once we start doing interventions, right? Once I say, oh, set like z to this value, then if we intervene z to be something, then here y will change. But here y will not change, because y doesn't listen to z. So that's why we need interventions to be able to tell apart causal structures as opposed to just Bayesian networks. But of course, we have this projection that I showed you between the layers. So from every causal Bayesian network, we can just forget about causal influences and just remember statistical influences, and we get a normal Bayesian network. But yeah, if we have this structure and what Pearl calls causal mechanisms, so I write down exactly like how z listens to x and how y listens to z, then I can answer interventional questions with this. How do I do this? Well, there's an operation that takes a causal Bayesian network and performs the intervention by, like, graphically or whatever. If you think graphically, you cut some links and you just plug in values. So there's this kind of surgical procedure that from M produces a new thing, M with Z intervened. And now here the data flow is cut. So if I intervene, Z doesn't listen to X anymore. And then what Pearl writes, something like P of Y given do Z, is just the distribution that we get under this new post-intervention causal Bayesian network. So this is a notation for causal quantities that we're interested in. And the way to compute them is to create the causal model and then compute it and look what we get there. Of course, the question is sometimes we don't know the model. How can we get to it? But if we have it, then this is the procedure. And importantly, so this do here, this is not a conditional distribution. This is very different from just putting here y given z, which is a rung 1 quantity. So an example from this, here is a very classic situation in empirical sciences. We have some sort of x, like a medicine which affects a treatment, y. But we assume that there's some common cause z here which affects both of these things. Then if we just condition y on x, we will not get the causal effect because there's this confounding factor there. For example, smoking and getting cancer and age. So if it was the case that just older people smoke more and they get more cancer, then by conditioning we learn nothing. So what we need to do is somehow compute away the influence to get to the quantity here that we're interested in. And in this case, if we know the distribution, then actually we can find a formula which is called an adjustment. So we compute sort of a joint conditional here with x and z, and then we average over the z's with the frequency that they occur. The formula is not important. The point is there exists a formula with which sometimes we can compute causal quantities from observational ones, but only sometimes, right? And this is what's meant with identifiability. So identifiability means under certain circumstances, a certain causal quantity that I'm interested in, I can compute it in some way from information that is further down the ladder. So in the mathematical sense, this means it descends really as a function. So here my intervention is a function which takes a causal model to a causal model. I can take a causal model and project to just get a distribution. And then sometimes, right, there exists a way that I can go directly from distribution to distribution by doing this. So if a factorization here exists, then we speak of identifiability, but it really might not. So a classical situation is if I have just X and Y smoking and cancer, and there's some sort of hidden factor which confounds everything, and I don't know what that factor is, and I have no assumptions about it, then I'm out of luck. I really, like, if I just know P of X and Y, then I cannot identify P of Y given do X, because there's many different causal structures which are consistent with my observations, but they would predict very different things under interventions. Sometimes though, and this is where stuff gets to be really interesting, if I make more assumptions, so this is very famously, here I have hidden factors that I have no control about, and I have smoking and I have cancer, and there's some sort of intermediate quantity here, so often something like tar in lungs, and the assumption is here that I assume that smoking affects cancer, but the whole influence is entirely mediated by how much tar we find in people's lungs. And this is a quantity we can measure. So now if we can measure the joint distribution of x, t, and y, but not hidden factors, it actually turns out that the hidden factors don't matter. We can identify this effect by a more complicated formula, which is kind of magical. So this is one very interesting direction to find out when things are identifiable. And Pearl has sort of answered his own question. So he came up with a system called the do calculus. And it's really strange to read as a computer scientist, because it seems incredibly informal. Like it manipulates sort of formal expressions where you have some probabilities of variables and then you can write do somewhere, and you have rules for manipulating them that are sometimes like the normal rules of probability. There's algebra, but there's also some graph theoretic assumptions. And then once you're done manipulating expressions, then sometimes the do goes away, and then you've identified the effect because you can compute it. This is the talk that we had earlier. And so Pearl says this is also, so it's sound, but it's also complete in some sense, right? So you can derive something in do calculus if and only if there's really a very strong unconditional notion of identifiability that doesn't assume anything about the model. So this works for any factorization. If you want to assume that there's, I don't know, things are linear, then you can do much more. There's this whole notion of partial identifiability, where even if do calculus says you can't, then sometimes you can still do a bit. But do calculus, if you can derive it, then you have this very strong identifiability statement. So that's cool. So this is something to keep in mind. And then there's this rung 3 stuff, counterfactuals. So then we want to think about hypothetical situations. So there's a real world where I observe some stuff, and then I create this counterfactual world in my mind where there's also random variables, but I want to relate the counterfactual world to the real world. It should not differ, in wildly weird ways. It should kind of have this all else equal. But people argue what this means philosophically, or in our case, we just need to be very precise in kind of specifying what all else equals means. So we need to say which random variables get shared in the counterfactual world and which variables get resampled. So to give you an example, Yeah, here's some code, so let's go through it. Here I say x is a coin flip, and y is just x, unless an error occurs with some small probability, and then we XOR this here. So y is x unless we flip. Okay? And on this side, we have almost the same thing. It also says y is x, except when an error occurs. But we have two different errors. We have here the error 1 only matters if x has 1, and the error 2 only matters if x is not true. I think this is strange, because on the level of joint distributions, this completely doesn't matter. You don't see if there's one or two sources of error. We just see how y is almost perfectly correlated with x, except for 10%. Those programs even react the same to interventions. If we intervene on x, okay, yeah, y will listen to it. It's the exact same causal structure, but it's a different counterfactual structure. So the amount of sources of error that we have really matters. If I ask you this question, so given that x is 0 and y is 0, what would have happened if we set x to 1? Okay, let's see on this side. If x is 0 and y is 0, then this implies that e must be 0, right? There cannot have been an error, otherwise we would have seen 1. But if there's no error and I set x to 1, then y is 1. Okay, that's easy reasoning. What happens on this side? Okay, if x is 0 and y is 0, that means there cannot have been an error 2, because otherwise we would have seen 1. But now if I set x to 1, then there's this whole different error that we have no control over, so we will see y with 90%. That's weird, right? So we have two programs which are very similar, both as joint distributions and as causal Bayesian networks, but they behave different under counterfactual queries. So which is why Perl solves it in this way. Perl says if you want to solve counterfactual queries, you need to be really explicit and make everything deterministic and kind of pull out all your randomness into explicit variables and then proceed deterministically. So a structural causal model is this. You have a bunch of independent variables, which are these u's. Think of them as errors, and the errors are independent, and you have priors on them. And then you have a bunch of dependent variables, in this case x and y, and the dependent variables are defined in terms of independent variables and other dependent variables. So for each of them you have a defining equation in terms of deterministic functions. Okay, fine, it's something we can do. I find it very specific that you need this amount of determinism to answer counterfactual queries, but at least it works. So if you write down everything like this, then you can answer counterfactual queries by taking your query, then you manipulate this model, so you can write down what the real world is, what the counterfactual world is, then you figure out all the distributions and kind of press it through. And of course, if you have a structural causal model, you can also project it down to a causal Bayesian model by integrating out all these variables here, and then you get distributions. Okay, that was the math part. This is how this is done on pen and paper, but we want to program, right? We want to have causal probabilistic languages. So what is causal probabilistic programming? It is a probabilistic language which supports causal queries, either interventional or counterfactual. It's as easy as that. Either it supports it or it can kind of reason about it internally. And what's important is we want this to be a general purpose language. We don't want to write a framework for structural causal models. I mean, these things exist, they are fine, but we want to do probabilistic programming, so this should be, I don't know, ideally Turing complete, or at least very flexible. And what are the goals of this? Well, first of all, talking about causality is really confusing, like even in normal conversation or on paper or writing it in do calculus. Like it's really a mess. So programming has the advantage that it's very clear and it's very operationalized. So I already hope that we get clarity, we get insight from developing these kind of languages that we want, and we get lots of tools to aid us there. So we get type checking, we get rung checking. What do I mean by this? Just to say the kind of thing you're interested in. On which level of the hierarchy is it? Is it an observational quantity? Is it counterfactual? Is it interventional? This is surprisingly subtle, I looked into a discussion online that discusses heredity. So these weird statements that always go into the press, like, oh, intelligence is 180% inheritable. And it's not an error that I say 180. These percentages can be above 1. So you're like, what is this weird definition? Part of it is that people don't disagree on which rung this is. If you check it, it looks very much like it's a counterfactual quantity. But then you look into the literature and there's a book arguing, like the whole first section, just saying that, no, it's a rung 1 quantity. It's actually not counterfactual, even you think it is. So this, I find this fascinating, like just having a kind of type theory that tells us where the quantity that we care about lives, eliminates lots of confusion. Then if we don't know causal structures, then often we want to do inference over possible causal structures. So there's a very higher order thing going on here where we would like models, causal models, to be kind of first-class structures in our language. So those are all great goals to have just in terms of clarity. But then, of course, we also want to automate. So we want to write a model once and then kind of do this whole causality workflow automatically without having to like open things up again or do it by hand. And we also want expressivity, right? If we can just write an SCM by hand, okay, then this is easy, but this is often not nice to do. So those are the goals for causal probabilistic programming. And then, how do we actually use these things? What's interesting is that there's kind of 2 different workflows that I've found so far in terms of what we have. The first one of which is we have actually a fully specified causal program. So it's completely runnable, there's no holes in it. This seems restrictive at first, but then remember we're kind of Bayesian, so whenever we don't know something, we can just put a prior there and kind of run it and then learn. And yeah, maybe the advantage of this is that it's immediately runnable, and we don't need to worry about things like identifiability, because we'll just learn something and we'll predict something. Of course, if we do nonsense, if we try to learn an effect that is not identifiable, then the result will be meaningless. So we'd still need to think about it. But at least in terms of the language, we can run it. So then you're in this whole idea of kind of Bayesian analysis of causality, which is maybe not the traditional way of doing it, but it's very compatible with programming, and it's something that has received attention. Or we leave holes in our program, so we admit that some mechanisms are unknown, and then what we really want to solve is a lifting problem, right? We want to ask a query about a program that is like on rung 2 or something, but all we have is a program on rung 1, and we want to add something. We want to add annotations or information or something such that we can answer the question. And to solve the lifting problem, usually we have to do math, so then we get into like rewriting what you guys talked about, or interactive theorem proving. I'll say something about this at the end. I'll mostly be concerned with this though, because this is nice as a language that just runs, and the 2 examples that I'll show there of this form. So let's get started. What's nice is that by virtue of programming, we're actually kind of already causal. It's a program. It's written sequentially, and like variables downstream listen to variables upstream. If you have stuff like reactive programming, this is very clear to you. So actually, in writing down a program, I'm kind of writing a causal program without even thinking about it. To pretend that it's all observational and that I can reorder lines all the time is unintuitive. So it's nice. And then I can actually identify causal Bayesian networks or structural causal models with just very simplistic programs, right? As essentially a list of assignments. So these things that I've shown before. Yeah, okay, that is a structural causal model. I've even written it as a program. So I can say that I have a sort of base case against which everything else needs to compete, and the base case is these very simplistic programs, and then on them I can solve my interventional or counterfactual queries by program transformation. We've seen this also some time, but so there's papers in this vein. They're like you come up with some sort of DSL. I think this one is in Julia, and you do the program transformations, and this is fine as long as you're sitting in this fragment. So here's an example. This was this XY example from earlier, and remember I wanted to say write X x and y are 0 and I set x to 1. So I have this little workflow where I say I take my program, now I need to twin it, so I need to create the counterfactual world. So everything with a prime here is counterfactual. I introduce this and I introduce a y prime. Then I need to do the intervention, which what it does is it just sets x prime to 1. And then I need to condition on my factual branch, which are usual observed statements. And then this is a probabilistic program that I can run and I'll just get an answer. So this is the basic workflow that I can do if I'm in this base case fragment and I want to do program transformations. But that might not be what we want to do. That might not be sufficient, right? Because the SCM fragment is very limited and we have a full high-order language around it, and I want to write flexible models. So then the question becomes, how can we do this whole thing compositionally? How can we do causal queries in a way that, of course, like we can expose the entire source code and try to mess around with that, but that's never nice and doesn't compose very well. What we want to do is to expose just a tiny amount of extra intention of our program so that we can use it to answer the queries. And to kind of come up with what we need to expose, this is exactly the challenge. And I can't tell you what it is, but I can give you some indications of some things that have been tried and that work more or less. But in the end, the problem comes down to this. We want to intervene at certain points, and we've called them intervention points, and we need to identify locations in programs. This should be user choice, by the way. Like if I have a program that does not expose any intervention points, that's completely fine. I just don't want you to like intervene on the internals of my thing. So I need to make a conscious decision. Here is a place you can intervene, and I somehow need to expose this, and then you can use it in your causal workflow. But how exactly do I identify these points? How do I expose them? There's lots of questions. I can do everything statically. It's kind of static analysis thing. This is already not bad. But then the question becomes, can I be more dynamic? Do I want everything to be fully typed, or am I more like just run and see what happens? Then very subtle things like, do I want to allow interventions in interventions or models that can like counterfactualize themselves? Sometimes this runs without problem. I wonder if this is meaningful. But yeah, those are decisions to go into. And then there are these kind of technical approaches to how do we make this work. And I'll show you a few of them just as glimpses. So some of them are just we name everything, or we use algebraic effects, or we use grading. And grading is the one that I've worked most on. So I will say a bit more about this. But so for a brief overview, so one of the first languages to do this is Omega here by Zena et al., which is a very interesting language. It essentially uses dynamic scoping to do counterfactuals and interventions. So you have a little do operator which you can apply to programs. And it does what you think it does, but then if you think about how it's implemented, it's actually pretty weird, because it will evaluate this expression, but everything is very lazy and very dynamically bound. So all expressions kind of remember the environments under which they were computed. And then you hit y, and now you see, oh, but y should actually be x plus 2. And then you can walk this lazy expression and say, oh, y was assigned here to x plus 1. Ah, no, replace that by x plus 2. So this works, but it needs a complete rewiring of evaluation strategies and so on. And I have no idea how to type this, because like how would you even do that, right? You need to go into expressions and kind of know what was in scope inside of the expression. So it's also a bit strange. Then another language that has been created here is Cairo, which, as I mentioned, sits on top of Pyro and relies heavily on this Python effect system that was created already for Pyro. And it also relies on vectorization in a very deep way to like encode interventions and branchings. And then work I've been doing in this collaboration was kind of to disentangle all these different things that go into one in Cairo. And we have a Haskell port kind of this that makes it a bit clearer what's going on. But in the end, what's the idea? So the idea is to use an effect system to specify essentially what happens to sample statements. So you already know, like here in rung 1 probabilistic programming, if we write sample, it can mean very different things. So in this paper, this is called modes. Sometimes when we see sample, we really want to sample. But sometimes when we see sample, we later want to give evidence, and it should actually just induce a factor statement or something. Or in this case, sometimes if we say sample, what we want to do is create an intervention point and intervene there. And one way to kind of change dynamically the meaning of what sample means in a program is to use effect handlers, because then later we can say handle this by sampling, handle this by factoring, or handle this by intervening. So this has been used in Cairo, but then of course this doesn't solve all the problems, because now your effect system needs to deal with the problem of tracking intervention points, and you have type systems for effects, so there's stuff like row polymorphism. You get pretty far in COCA if you try to do this, but then I looked up somewhere and they say that COCA doesn't have answer type polymorphism, which is where you get stuck. That's all I know about this. Then another thing is also, if you want to be more dynamic, then you need to think of generating instances of effects kind of on the fly. Yeah, I'd love to understand more about the effect picture and have a type system for it. I mean, so if you want to remember, the question here is, intuitively an intervention point is very similar to a delimited continuation, because you just, at the point where you sample, you remember, oh, here's a point, I can go back later with like different data and then run again. And if you want to type delimited continuations, it's a similar kind of mess. So this is the first thing. I mean, there are type systems for delimited continuations, but do they solve this? Type theoretically, probably. Now, is the semantics correct? We've had disagreements about this, because is an intervention just a delimited continuation? Maybe, but for counterfactuals it gets weird, because you interact with the world and some things should not run again, but then some things should be taken from data you've already computed. But yeah, this is one direction. Then a very nice direction is to use traces or make traces explicitly. This is already something we do on rung 1 probabilistic programming all the time, right? So if you think of your basic MCMC, you have kind of two choices how to generate a proposal. One is to just pick a point in your trace and resample, and then run the entire continuation again to like generate all the choices. If you think about this, so this is an inference algorithm for a rung 1 problem, but it's kind of using an interventional approach. You use causal structure of the program. So this is, I don't know, this is causal MCMC or something if you want. Then you figure out that this is not very efficient, because you make big steps, you regenerate lots of stuff. So you can improve this by just picking a site and just changing that site and keeping everything else as it was, and then accounting for it with the factors. But that's counterfactual. That's like the natural direct effect or something they call this, where you say, oh, I keep everything the same and I just change one quantity. So you get these kind of anti-causal or counterfactual traces. I don't know if that's useful to think about, but I mean, it tells us that traces could play a part in causal programming. And I mean, Alex has typed them. And what's also interesting is that if you make a probability monad with explicit traces, then so you guys point out that this is a graded monad, and indeed grading is a very cool idea. So a graded monad is like a monad, but you attach a tiny piece of information that tells you a bit more about your effect, and you track that statically. So you grade in a monoid or something, and then you have a return which says for every x you can make a computation that is graded over nothing, so it's free. But then if you bind computations together, their grades multiply. So the classic example is, instead of using the list where you have any amount of non-deterministic outcomes, you can use the graded list monad, which is graded by natural numbers, and you know exactly you have n outcomes, right? Then the return says you have exactly one outcome, and if you sequence two computations that have one has n and the other one has m outcomes, then you get n times m outcomes because they form the Cartesian product. So this is a classic way of kind of fine-graining effects. For the samplers, we have the same thing. So there you grade over the trace type, which is this record of all the samples that you make. And if you sequence two computations, then their grades union. And for interventions, we can do something very similar. And actually, that's quite simple. So I wanted to put this here. So for interventions, I grade in intervention points, which, to be precise, I grade in just list of types. And this list enumerates all the intervention points that I have in my computation and what their types are. And now what's a monad? So to give an intervenable computation with return type x and intervention points a1 to an is to give this function. Well, it takes all the arguments a1 to an and outputs a distribution over outputs. But instead of taking n inputs, for each input I now have a maybe input. So I can either give it a value, which means I want to intervene there, or I give it none, and that means keep your original data flow. So very, very simple definition. And then here, yeah, indeed, if I have these lists of intervention points, they just concat. Fine. Yeah, that works. I can, if I write this as a program, the way to generate this grading is to have a little primitive function int, which means create an intervention point. So it takes an x and also returns an x, but also creates an intervention point of type x. So it has this funny graded type. And what does it do? Int x, well, if we call it with none, it means just take the original piece of information that was there. But if we call it with some new value, then you take the new value. So very, very simple function. And like here's a program in this graded monadic style. So we sample, I don't know, some hidden factors. And then I sample if the person smokes or not. But I also create an intervention point. So this program will have return type h times s, but it will also have grade s, meaning I can later intervene on the value of whether this person smokes or not. And grades are also cool because there's independently a lot of recent interest in this. So Sam has had a very nice paper with Jack here where grading shows up in imprecise probabilities. So there we have two sources of randomness, kind of probabilistic uncertainty and Knightian uncertainty. And they don't interact well in, like, if you put them on the same footing. But if you put one of these randomnesses into the grading, then it all works out very nicely. And there's also a kind of string diagrammatic way of drawing graded string diagrams, which actually, this is not from the paper, this is stuff that I drew independently, and they are completely the same formalism. So here this weird plus to me means create an intervention point. Data flow goes up, interventions come from the left. So here we have a program that has two variables, and you have two ways of, you can intervene here, right, and you can intervene here. And then there's some equations. For example, if you shuffle data flow around, you also need to shuffle interventions around. And and here to perform the intervention, you draw this as kind of bending the wire, right? So here data flows up, but if you say take instead this value, then you discard this one and you take that one. I don't know if you care about graphical algebra, but if you do, then it's very simple and it's very nice. So I think grading is a very nice idea. It's something that we managed to work out that is nice. Because for lots of questions we don't know how to do it, but if we want to do statically determined rung 2 causal probabilistic programming, I would say grading solves it. Now this is restricted, so we can ask, can we make things more dynamic or generative or first class, which grades are not. Grades are static meta things. So this is still open, but at least it does what it does. Now let me see how much time I have. Perfect. A bit of theory to torture you at the end. So I have avoided category theory so far, but of course this is kind of what I think about is we have SEMs, And I really want to get a handle on what they are structurally, and this isn't very known. So one thing that would be nice is to say SCMs take independent variables to dependent variables. So can we make them into a morphism of some kind from independent to dependent? And this seems nice, but then it becomes really weird if you try to do it, because, okay, independent variables are fine. They are very clearly in the domain of whatever morphism this is. But dependent variables play a kind of double role where they are outputs, but they are also a bit like inputs. And actually the intervention operation takes here an output and shuffles it to be an input. And yeah, it really has these both roles, which I think category theory doesn't like, or at least I don't know the kind of category theory that accepts this. So I've tried stuff like hypergraph categories. This is things where you can bend wires, so like relations, where you can make inputs to outputs. But those things are very symmetric, and this is not symmetric. Interventions are not symmetric. So it doesn't satisfy this. Maybe it's a weird kind of skew hypergraph category. No idea. But hey, we can write it like logic, so we should solve it like logic. I've also tried polycategories, which is a more linear logic-y thing. So there you say we have two different connectives, right? So in linear logic, this would be here tensors and here pars, which it makes sense that we should use different connectives here because, again, input variables and output variables are not symmetric, so they should compose differently. But it's also not a polycategory. So yeah, I don't know what this is. This would be very cool to just give a name to it. But so far, we don't know how to make SCMs into morphisms. We can do the next best thing. We can make SCMs into objects. Just means they're an object of my category, and then I discuss what a morphism of SCMs is. And maybe that's interesting. So it turns out some machine learners have proposed very recently a definition of this. This isn't even SCMs. This is a Rung 2 paper. They say what's a kind of mathematical model of something that reacts to interventions. They call this a causal space, and derive a bunch of stuff. This paper is relatively nasty to read because they just use lots of measure theory that in the end doesn't matter. After a long time, I figured out that if you write this in a category, a causal space is exactly a morphism of this shape. Now, if you squint at it, this is exactly the grading that we used, right? So we have n variables that come out. So it's something that takes n input variables, but for each variable we can say intervene or not. And it also gives n output variables. Now, this accounts that exactly what I said before, right? These variables play a double role. So they kind of show up on the domain and the codomain. And we have different monodal structures, and we have self-grading. So it kind of all ties into the things I've been saying, which I found very nice. And I mean, I much prefer this definition over this. Also, if you like dependent types. So for interventions, we just had to grade here, and we just say +1 everywhere. So this is a non-dependent, I don't know, you can implement this quite easily in any of your favorite languages. If you want to do counterfactuals, it seems to me things get dependent a bit, but they get very, very slightly dependent. So here's a rock definition. This is essentially the maybe type, right? So I say something of type default A either has value default, that is like none, or it has value novel, which is some. But I've also attached just an extra default value to this type that tells you, oh, in case I say default, you actually mean this. This type is isomorphic to maybe, but in a weird sense that is still slightly dependent. So that if you use this, you can write something here that looks a lot like an SCM. So in this definition here, which is a dependently typed function, it has independent variables x and y, and then it says z. Well, z is also like a variable, right? But it has default type x plus y. So if we say nothing to z, it will have value x plus y. But if we want to intervene on it with, I don't know, 52, then it will be 52. And this is a dependent type because, yeah, the type here depends on this expression. So, yeah, I believe that this silly kind of default type theory actually gives us a way to define a category of SCMs where essentially, yeah, we're doing dependent type theory. There's an analogy with automatic differentiation that I really want to understand. I think this is probably something that people know in like a folklore way, but I can't say what the precise formal connection is. So in causality, right, our base truths are these SCMs. They are a class of programs. It's the same thing kind of as an autodiff where we say the base truth is a computational graph, which is also a very kind of simple program. And then we run backprop on it. And backprop, mathematically, what it should do is compute the derivative, right? And then, so rung 2 interventions in causality seem to me very similar to computing total derivatives, and rung 3 counterfactuals kind of compute partial derivatives. I don't know, you can glance at this, but we don't have time. I don't know if this is true in any formal sense, but what's nice is that for autodiff we have these nice differentiation macros that extend this to higher order languages. So maybe this is what we're looking for. Like if we understand this analogy, then here can be causal probabilistic programming. Yeah, category theory, okay, Markov categories are nice. We have a paper where we do things in string diagrams, which is great because it's the semantics version of what you guys did with syntax. So that's very nice. And here's the last thing I wanted to show you. So I happened to code up Markov categories in the Unimath, which is a project like homotopy type theory project in the rock proof assistant. And then I had the definition, which was kind of there for fun, and it was like, oh, what can I prove with it now? What's cool? And actually, I can prove identifiability statements. So here, like you can go to my GitHub and just look at this file. But what's the type of statement here? So I define what I call strong conditional identifiability, and it's just a definition like this. So it's the lifting problem, right? I have something on rung 1, and I want to ask, does any choice of lift here compute the same quantity? And then here's this classic example of like, so this is the backdoor adjustment formula. So X affects Y except Z confounds it. And I want to prove that I can compute the causal effect by adjusting for the confounder. And yeah, so these statements look horrible because this would be much better graphically, but we don't have it. So it's just algebra. So it's ugly. But what's also nice about it is there's no measure theory in it. There's no numbers in it. This is as formal as it gets. Like this is pure algebra. Markov categories are the kind of algebra of composing probabilistic processes. So I can define what my model is. Do you see it? Yeah, so the model just consists of three maps. This is a factorization. Then I say what the joint distribution is of a model. I say what the interventional distribution is of the model. And then I want to show that if I have a certain full support assumption, then from the joint distribution I can identify the interventional distribution. And I have to prove it. And yeah, then there's like, I don't know, 200 lines of shuffling this algebra around. But as a formal statement, I found this really nice because we can just prove it. And this assumes nothing. Like it's a pure Markov category with conditionals. So continuous, discrete, you name it. I think this is a very nice thing that category theory can contribute, is to give very formal proofs of these identifiability things. Is it complete? I don't know. This would be fantastic to show that I can do calculus in rock or something. Yeah, so I hope to have gotten you excited in causal probabilistic programming because it's here and people are interested in it and it's exciting, but there's lots of challenges. Let's work on it. Thanks.
Yeah, thanks for the great talk. It was super interesting and also made the concepts a lot clearer to me. I was wondering about your ROC implementation. You said you used the homotopy theory version of ROC. Yeah. Do you make use of homotopy type theory like features?
Not. It's
okay.
just because my co-author was interested in the homotopy definition of Markov categories, but it does not matter.
Okay, I was just wondering, yeah.
It's just what I have.
Whenever I see A plus 1, I think, is that A plus bottom? Have you thought about doing any kind of like domain theory here, or thinking about, you know, it seems like in this interventional stuff, it's saying you have different levels of knowledge about your variables, and you're saying, if I forget something about one of the variable, what gets reconstructed? Okay, okay, okay. Sounds good.
Thank you. Thank you for the interesting talk. I don't know if this is the right question to ask about, maybe since this is an introduction to the field. Is there there's some sort of expressivity questions you talk about? Is there some sort of problems you have in mind as sort of application fields or like benchmarks where you can say, yes, we can express this sort of stuff using this framework? But of course, just the mathematical connection is sort of interesting by itself. But that's sort of another question that comes to my mind.
Yeah, if you want to go practical, so from languages that exist, I mean, Cairo is the strongest contender, and on the Cairo website there's a very nice set of kind of progressively harder tutorials. Yeah, have a look there. So this is what we do in our Haskell port, is to see, oh, now I don't know, the simplest class of problems we can replicate it, but then suddenly, I don't know, this uses a weirder kind of, especially with counterfactuals, you can get very weird because you can like plug in arbitrary expressions or create new variables. So it's kind of, we start out with a very simple model and we see how far we get, and then suddenly it's not expressive enough to do this application. And then we're like, should we modify it? Is it worth the pain? But then maybe yes. Those are the right kind of questions to be asking. I think for this, yeah, look at the tutorials, look at the kind of things people want to do, and then see if you can do it.
Cool. As a follow-up, so then the sort of language design perspective is that you're trying to give more grounding to the sort of stuff that happens in Cairo and sort of make it safer. Is there sort of from that perspective? Are you looking from that perspective, or sort of just giving more mathematical foundations to what's happening?
No, there's different avenues, and I try to do several of them. I mean, I'm a very mathematical person. Like I like the theory, but I also like understanding Cairo. Those are separate projects. But I mean, maybe if we find a good answer in one, then it might inform what we want to do with the other. But I mean, you have the. Now you have all these people trying to do counterfactuals with LLMs. So what goes in there? You have Python code or some sort of library that computes something, and then they rewrite everything as SCMs and do it by hand. You shouldn't do that. You should have a language where you take the existing code and it's capable of, like, I mean, the way autodiff works. I think autodiff is a really nice. You don't want to go through your code and compute derivatives by hand. There should be some sort of formalism that takes what's written and then lets you answer these questions.
Yeah, I think that's a good comparison. Great, thank you very much.